Okay, so as I said, the actual size of a hydrogen atom, not its de Broglie wavelength when it's moving at some particular with some particular momentum, just its sort of characteristic size as dictated by its lowest energy electron orbital. Okay, has a characteristic size of about an angstrom, that is 10 to the minus 1 nanometers. Okay, and so which is 1 angstrom, and so this electron wavelength at these energies is much smaller than the smallest atom. Okay, and so for all intents and purposes, it's going to behave as a particle, not as a wave, because unless it's except for if we consider scattering off the nuclei of atoms, which can have dimensions which are much smaller than this even, it's basically going to look like a particle. Okay, so that gives you the scale. So the Davison-Germer experiment was the first experiment to show that, in fact, we could think of matter, in this case electrons, also as waves. And what they were doing is they were studying the reflection of low energy electrons off of nickel crystals. And so here's kind of a schematic of the experiment. Over here we have some electron gun, and they were using low energies. As you know, in a modern electron microscope, again, you have sort of something on the scale of 100 kilovolts of voltage. Here they had about 54 volts, so much smaller. So they were accelerating these electrons, and then they were basically directing them onto a nickel crystal and looking at the electrons reflecting off this crystal and they had a detector which could actually measure the number of electrons per unit time. So that is something proportional to the intensity of the electrons as a function of the angle here, the scattering angle between the beam that they shine on, the electron beam that is impacting the nickel crystal, and again their detector direction. And what they found, which is kind of indicated by this sort of darkened curve here, is that the probability or the intensity of scattered electrons actually had a peak at a particular angle for this particular voltage of 54 volts. Okay, so you wouldn't necessarily expect this. You might expect that electrons sort of reflect off the surface in roughly random directions, because the surface isn't going to be exactly perfectly flat, and so it's going to, electrons are going to kind of, if you think of them as particles, you'd think that they were kind of bounce in sort of random directions. Probably you would expect that the largest reflection, the most probable reflection, would just be back in the direction from which the electrons came, and they certainly found that too, but they also found this peak over at an angle of 50 degrees. Here, this little red curve here is a little confusing, so I've redrawn it over here in just sort of a graph of the electron intensity of scattered electrons versus the scattering angle phi. Okay, and so again, they see something which peaks up, which is the most probable thing to happen is that the electrons just reflect back, but they also saw this peak at 50 degrees. Okay, so that's what they observed in it, and this observation, as we'll see, can only be explained if de Broglie's hypothesis is true, namely that electrons can be considered as waves. Okay, so how do we explain the Davison-Germer experiment? We have to invoke the concept of Bragg scattering, which usually is actually discussed in terms of X-rays, X-rays which are high energy photons, very high energy photons, very short wavelength photons. But we can use the same formalism if we assume that de Broglie's right and that electrons are waves. We can test that hypothesis by assuming that they're waves, seeing how if this peak can be explained